Light is a form of electromagnetic radiation. At some wavelengths, it appears as visible light. At others, it takes the form of radiation we cannot see, such as ultraviolet, infrared, and X-rays. X-rays are very short wavelengths, ranging from 1 to 10 nanometers, and unlike visible light, are able to pass right through most tissues in the human body. Since bones contain calcium, a denser material than most other tissues, they are able to stop some of the X-rays and can thus form a shadow. If you place your hand in front of a torch, it will cast a shadow on the wall behind it. In a similar manner, X-rays directed at the body produce shadows on the opposite side that can be registered on film or on a digital sensor, so that bones are clearly visible while soft tissues, such as muscle, are shadowy. As a result, the two-dimensional images formed by the X-rays are quite useful in revealing structures within the body and can easily display fractures in bones. In 1895, German physicist Wilhelm Röntgen was experimenting with beams of electrons inside a vacuum tube. He covered the tube with cardboard to keep any light from escaping, but noticed a fluorescent screen nearby light up. He theorized that this glowing was caused by an unknown invisible form of radiation, so he called them X-rays. Röntgen conducted further experiments and discovered that X-rays could travel up to meters in distance and could pass through certain materials such as cardboard, but not through denser materials such as bone and metal, which absorb the rays. This meant that denser materials made imprints on photographic paper. The very first X-ray was of Röntgen's wife's left hand. Röntgen's findings earned him a Nobel Prize and paved the way for the use of X-rays in medicine. The heart of an X-ray machine is an electrode pair composed of a cathode and an anode that sits inside a glass vacuum tube. The machine passes current through the cathode filament, heating it up. The heat causes the electrons to fly through the tube towards the anode. When an electron collides with the rotating anode, it releases energy in the form of an X-ray photon. The entire mechanism is surrounded by a thick lead shield. This keeps the X-rays from escaping in all directions. A small window in the shield lets some of the X-ray photons escape in a narrow beam. The beam then passes through a series of filters on its way to the patient. As the X-ray energy passes through the patient's body, the photons of the beam reach the film and cause a chemical reaction. The areas where X-ray energy passes through the body appears black, while the areas where X-ray energy is absorbed appears white. This produces what is commonly known as an X-ray image. Nowadays, the resulting X-ray energy is registered on a digital sensor, rather than on film. This X-ray imaging technique is also applied in computed tomography, where an X-ray beam is rotated around the patient's body. The scanner produces images in thin slices, which a computer then reconstructs into sharp, three-dimensional images of the scanned body part. Mammography is another special type of X-ray imaging used to create detailed images of the breast, and is commonly used in screening for breast cancer. Fluoroscopy is another method that shows a continuous X-ray image on a monitor, much like an X-ray movie. During a fluoroscopy procedure, an X-ray beam is passed through the body. The image is transmitted to a monitor, so the movement of a body part, instrument, or contrast agent, such as an X-ray dye through the body, can be seen in detail. X-ray imaging is one of the fastest and easiest ways for a physician to view the internal organs and structures of the body. It is an excellent tool for assessing skeletal trauma, for diagnosing the gastrointestinal system, for high-resolution diagnostic imaging of the breasts, and for comprehensive imaging of the thoracic cavity, including the lungs and heart. A host of other applications for X-ray imaging are also available, including imaging the kidneys, teeth and jaws, and the fine structures of the ear, nose and throat. X-ray diagnostic imaging still comprises a majority of all diagnostic procedures done on a worldwide annual basis. X-ray imaging is helpful in the diagnosis and management of medical conditions, such as fractures, dislocations, cancer, and internal bleeding. It is non-invasive and the procedure is painless. Because X-ray imaging is usually fast and easy, it is particularly useful in emergency diagnosis and treatment. X-ray procedures usually require no recovery time, so patients can return straight to work or school afterwards. Significant exposure to X-ray radiation can cause cell damage, increasing the risk of developing cancer in the future. X-ray imaging procedures are usually not recommended for pregnant women, as it may have harmful effects on the fetus. More specialized procedures can be very expensive, costing up to thousands of dollars. Over 90% of all medical imaging examinations worldwide currently rely on X-rays. But the technology is still based on the fundamental principle of X-rays that was used over 100 years ago. In view of this, current research has been focused on developing ways to improve X-ray imaging. Phase contrast X-ray imaging is a new imaging method that is being explored clinically. Unlike conventional radiography, which measures the attenuation of a beam through a biological sample in order to determine its structure, phase contrast focuses on variations in density that change the phase of the wavefront of an X-ray beam. This same physical phenomenon can be seen in the light effects on the bottom of a water-filled swimming pool on a sunny day, as straight lines on the pool floor appear distorted. This phase shift is highly revealing, since it varies depending on the refractive power of the tissue through which the radiation passes. This approach would make it possible to distinguish between different soft tissues, which would be helpful in differentiating a tumour in an early stage of growth from healthy tissue. The use of phase contrast also has the potential to reduce radiation doses. Compared to attenuation-based X-ray imaging, phase contrast has a theoretical potential to reduce doses by 10 to 100-fold due to the inherently high contrast it affords. Researchers are also looking at firing electrons from a cold cathode ring made of nanostructured carbon that operates at a high voltage and at room temperature, rather than a hot cathode, which converts no more than 1% of the energy into X-rays. The advantage of this approach is that it yields more energy than previous cathodes. Some imaging systems use amorphous silicon-based X-ray detectors, which are made on glass, making them heavy and breakable. This weight also comes from the housing that is installed to cushion the glass from breaking in the event of a drop. Such housing can add cost and complexity to the X-ray sensor, which a plastic-based X-ray sensor will not incur. They also have the potential to be conformed to objects, thereby allowing a new range of applications that weren't imaginable using a rigid X-ray detector. Further advancements in X-ray imaging will continue to greatly impact medicine in the future and save lives.